So a pair of glasses like this, make sure you have them before next week. I have these big clunky ones because I wear glasses, so you'll need them like this if you wear glasses. If you don't wear glasses, there's kind of a more sleek style that's a little more comfortable. You don't need to get goggles, the ones that sit against your face. And you don't want those unless you have to because they're not very comfortable. So get safety glasses, not necessarily goggles. Okay, so we'll do lab stuff in a little bit. I'm going to do a little lecture, a little bit of lecture today. I've uploaded this PowerPoint. Okay, this moves into chapter 11. Oh, did you guys see the questions I put up on D2L? So that's practice for the test. I'll start building more questions on there. But for now, we'll move on to chapter 11. This is kind of a review. In 1211, you remember solutions? There was solvent and solute. Remember that? I know we went over that in my class. This book seems to have waited until here to talk about solutions. You guys know what I'm talking about? So it's a mixture. It's called a solution. The thing that there's more of is defined as the solvent, and the thing that there's less of is defined as the solute. If it's a 50-50 mixture, like you can mix 50-50 of water and alcohol, we just say 50-50 solution. And sometimes they're so close to amounts that the idea of solute, solvent really kind of doesn't carry over, so it's a little vague sometimes. But in general, there's a solvent and there's a solute. That should be So my second slide here, solutions can exist in any physical state, any of the three. We will generally only talk about liquid. So we've got a liquid solvent, and it'll be one of these two things. You've got a liquid solvent, and you put a solid solute in it, or you've got a liquid solvent, and you've got a liquid solute. But either way, it ends up, once you make the mixture, once you make the solution, it'll be liquid, at least as far as chemistry classes go. The other categories are like alloys for metals and things like that, but we generally won't talk about those. Third slide is just a few facts about solutions, and I think these are kind of obvious. The physical state of the solution is generally the same as the solvent. It will be in our cases, like you've got a liquid solvent, you put a solute in it, the solution will be a liquid for all our cases. I think all this stuff is obvious. Really, homogeneous and then number 4 on this list are kind of the same thing. But for it to be a true solution, the solvent and the solute have to be spread out evenly. There can't be like a little clump of solute down at the bottom and then solvent. Then it's not a mixture. Then it's not a solution. So it has to dissolve through the solution evenly. So we talked a lot about the intermolecular forces. That was dispersion forces, dipole-dipole interactions, and then hydrogen bonding. Now that we're talking about two different types of molecules, and it introduces the idea that one might be an ion and the other one might be an ion, and then they're attracted to each other. That's one type of interaction. We don't tend to talk about those because we don't talk about molten ionic compounds because the heat is so high, it's generally not something we do in a typical chemistry class. But the ion dipole tends to show up in these types of things. Like if you dissolve a ionic compound, it becomes ion in water. You've got the polar water, so it's got some positive and negative on the water. And then the positive part of the water will be attracted to a negative ion, and then the negative part of the water will be attracted to a positive ion. So that's the ion dipole interaction. Hydrogen bonding is also important when you dissolve one thing into another. Dispersion is actually important too. But ion-ion doesn't come up much more. What is this, the fourth slide? I can't get my slides to number. So this is the fourth slide here. This is just an example of what I just described. You see on the left side here, you've got a chlorine ion here. Well, really what happens, if you put solid KCl into water, it goes in as a chunk like this, the chunk down here in the middle. And then the water molecules kind of attack it and surround the ions and then pull them out and take them away into the solution. And you can see that the space-filling model for the water here, the red is oxygen, and that's where the slight negative charge would be. And you can see that these water molecules are oriented around the positive ion. And then the same with chlorine, except now it's the positive side of the water grabbing the chlorine. Does that make sense? And big molecules can dissolve in water too. This is sucrose. Sucrose, if I gave you just kind of a simple idea, it would be OH, OH, sometimes it's that, and then OH, and we fill in some, and really I should do this, because it's kind of, these tend to be long molecules. But the key is here, if I said this is sucrose and there's just lots of OHs along the chain, and then you've got water, the reason this dissolves is because of these attractions. Hydrogen to there, and here's another water molecule. Let me near an OH. So it's hydrogen bonding. So water molecule can grab on hydrogen bonding wise to this. So that's why the sucrose dissolves. And that's just what those pictures show. So it's the same intermolecular forces, going to the next slide, but we would say there's solute-solute interactions, like if I've got water, or let me say solvent-solvent interaction. If I've got water and I'm putting some KCl or something in there, the things to be cognizant of is the water molecules have attraction to each other. The solid KCl, those have an attraction to each other, basically the ionic lattice. And then, of course, the solute to solvent interaction. If you consider all three of those, I like to describe this with my hands, but the next 4 slides is, it helps to think of it like this. If you want something general to keep in your head, if I've got some particles, and let's just say I have a solid or something, but ignore that. I've got a compound, a copy of that same compound, they're all together. If you put energy in, this is intuitive, if you put energy in and think in terms of heat, they come apart. That's intuitive. It's not as intuitive, but it's the exact opposite. When things come together, energy goes out. But I try to describe on this slide, the next 4 slides, think of it like this. It's not really cause and effect. You can switch the cause and effect back and forth. If I have 2 things together, and then I literally tie a little chain to here and pull this way, and I tie a little chain to here and pull this way, like a mechanical force pulling them apart, if you do that, energy goes in. It actually goes into the particles. Now think of it like this. Energy goes in. I'm not physically pulling them apart with little chains. Energy goes in and it pushes them apart. So you can think of it as pulling apart is the cause and the effect is energy going in. Or you can think of it as energy going in is the cause and the effect is them coming apart. But either way, when things come apart, energy is going in. So when you try to think of it as cause and effect, sometimes it messes you up. But just realize things are coming apart, energy is going in, and the opposite. Things going together, energy comes out. If you can remember that generality, the rest of this kind of makes sense. So here I'm showing mechanical forces, the cause, energy coming out. And then I do it the opposite. Energy coming out, things move towards each other. I mean, think of steam. So you've got water as a gas. You could increase the pressure, which would force them together. The energy will come out. Or you could take energy out and cool it, and cool it, and cool it, and cool it, and then they'll still come together. Cause and effect different, but the point is when they come together, energy comes out. You can suck the energy out to make them come together, or you get some other effect to make them come together, energy comes out. You follow that? And then it just did the opposite. When things move apart, energy is flowing in. It doesn't matter what the cause of the effect is. And generally, very frequently, certainly with boiling points that we've talked about and the intermolecular forces, and in this case, solvent-solute interactions, it's pretty much always, but not always, positive and negative that's pulling them together. It's the electrostatic attraction. Ion dipole, 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 hydrogen bonding, it's always that positive, negative pulling them together. But it is important. Dispersion is important too. There's a small attraction due to instantaneous dipoles. Yeah, and in this case, I would say the electrostatic attraction is what's pulling them together, and then energy will come out. Or energy going in to overcoming the electrostatic attraction. So that's the way to think of it. And this helps to make sort of an energy diagram. Did you guys do energy diagrams last semester? I know we did in my class, but it seems like the book I was using didn't really do them. So think about it like this. You have your solvent, and you have your solute, and you're about to put it in. The solvent molecules have an attraction to each other, and the solute molecules have attraction to each other. And so as a starting point, so there's that, and now think later, you already put your solute in the solvent. What you've got is solvent molecules had to come apart a little bit, and then the solute particles had to come apart a little bit, just so they'll all fit together. See what I mean? You follow what I'm saying? Let's say it's water. So here's just the solvent molecule of water. They have this attraction to each other. And let's say it's NaCl. I was using KCl there. We've got so this is what ionic compounds do. I know I mentioned this in 1211 last semester for my student. But it's NaCl, NaCl, and you've got NaCl, NaCl, and then going out, picture right in front of this chlorine an Na+, and then a Cl minus Na+. That's the crystal lattice. That's a crystal lattice structure. So you've got these forces holding these together, and these forces holding these together. And then later, after you mix them, you're going to have the solvent molecules have come apart. See, that's the negative side, so that'll be and then these will have attractions to the Cl minus. So these have to come apart, and these have to come apart in order to get this situation. Follow what I'm saying? So one of the things that has to be overcome is you've got to overcome those attractions here thermodynamically, in a sense. There's energy in that, and then there's energy in that. And then here we are with a negative and a positive coming together. So what I'm saying is energy goes in to pull these apart, energy goes in to pull these apart, and then energy comes out when these come together, solvating them. You with me that far? If I diagrammed it, if I said this coming out is delta H1 solute, well, I'll do it the way my slide has it. This is pulling these apart is delta H1, the amount of energy it takes to pull those apart. Delta H2 on my slide is pulling apart the the solvent, and then delta H3, which will be the opposite direction. This is energy going in, energy coming out. You with me there? So it takes a certain amount of energy to pull these apart, a certain amount of energy to pull these apart, and then a certain amount of energy comes out when all these come together. So if I diagrammed it, I'll just do it in 2 stages. I've got, if I said, okay, energy going in, so I've got an axis like this. Energy, positive direction. This is delta H1. And then more energy for the delta H2. And those together tell you how much energy actually has to go in to cause this to happen. Let's say this is that energy level. And then when these come together, let's say delta H3 was that much energy. Overall, is this endothermic or exothermic? This much energy went in, but only this much energy came out. That amount of energy stayed in there. Huh? It is endothermic. Because at the end of the process, by the time you get through process 3, energy ultimately stayed in there. You see what I'm saying? You can also have this case. Where delta H3 is longer, and this would be, so which one is this? Exothermic. This much energy in, this much more energy in, but all this energy came out because of these awesome, strong attractions here. So you can have endothermic or exothermic as your process for dissolving. So that's what this is showing if you want to, slide 11 is just showing mathematically how it works out. If you take the absolute value of these two added together, if this is the absolute value of 3 is bigger than both of those together, you get exothermic. If it's smaller than those two together, you get endothermic. It tends to be true, you see this third one where no solvation occurs, meaning the solute you put in the solvent doesn't dissolve in the solvent. When that happens, you just put it in your solvent and it just floats down to the bottom and you can still see it. It didn't disperse into the solvent. It tends to be true if you have, the video back. It tends to be true that if this is really, really small compared to the first two, that tends to be a case where it doesn't dissolve. If this is true energy-wise, then it just doesn't happen. But if this is a bit longer, and sometimes way longer, those two situations, you can have this situation, I'll just say no, that if you have this situation, or if you have this situation, so delta 3, 1, delta H3, 2, either of those tend to happen, but this one's endothermic, this one's exothermic. You can feel it sometimes. There are some ionic compounds that if you put it in water, you can literally feel the water get cold. The water. You're holding a beaker and then you put the ion in there. The heat that it's taking, it takes it from your hand. That's what makes it feel cold. Or it just takes it from the ambient room and energy goes in. This one, if you dissolve, you can get NaOH in a solid form. If you put that in liquid, it gets really hot. Because so much energy comes out from the ions being attracted. Na and OH, if it was a sodium hydroxide. Still recording. What else do I have here? This is in general true. We usually say like dissolves like. So maybe this is obvious. Let's see here. If you do something like, certainly ionic compounds will dissolve in water. Some ion compounds don't dissolve in water. But let's say it's a molecule. I'll just do, here's an OH. So this is ethanol, as in drink it and you get drunk. Alcohol, ethanol. If you put that in water, it does dissolve very well, very easily in water. If you just set it in a word, what do you think that word is? Why it dissolves so easily in water? These do have to come apart. Delta H1, these have to come apart. Delta H2. Delta H3, they really, really get pulled into each other. And delta H3 is a very long arrow going down. What would you say is the major attraction going on there between these? Think intermolecular forces. Hydrogen bonding. Lots of great hydrogen bonding between the water molecules and this alcohol. So that's why that arrow down goes so far, because it's really pulled into each other. You've heard oil and water don't mix. Heard that before. In some sense, what oil is just really long hydrocarbons like this with no OHs or anything else. Carbon to carbon bonds are not polar. Carbon to hydrogen bonds are not polar. So there's no polarity here. And then you try to say that's the solvent and that's the solute, but it doesn't matter. You can try to do 50-50 solution. You might think to yourself, well, this has dispersion forces and this has dispersion forces. Why don't they dissolve just because of that? The reason is because this is a polar solvent, or the water is polar. It's this. Remember, the first thing that has to happen is that these molecules have to come apart and these have to come apart. And the thing is, the water attractions, I want to do them. At least get one more water. Those attractions, no, that's not one. Let's put another one here. Anyway, any water molecule is so attracted to all these other molecules. It's like if you had a blob of a bunch of these that were, you've got them in a beaker, so already their dispersion forces have them attracted to each other into a liquid. And you try to put that in there, the water molecules just kind of squeeze themselves together. And then even if you had separate blobs of oil bound in the water, here's your water, here's blobs of oil. The water just is sort of squeezing them out. So water molecules are around here kind of squeezing such that these have to stay together. And over time, these little blobs will find each other, and then they'll stick. And a little more time goes by, and this one floats around, and it meets this one, so you got a little bit bigger blob. And enough time goes by, all that oil, and generally it happens pretty fast. I'm making it sound like it takes several minutes. But eventually, all those blobs of oil end up together because they're sort of being excluded. The water's squeezing. So even those weak forces aren't what pull these together when it's in water. It's these strong forces that are squeezing the oil out of the water. So it can't be in between water molecules. So that's why oil and water don't mix. You'll end up with this. Surprisingly, well, maybe it's not surprising. This is less dense than water. So over time, what you'll have is denser water and less dense oil on top. But the reason water is so dense is this. It's pulling them together so strongly. Make sense? I don't really have questions up on this solubility stuff yet. What I would go over for this next time, this is just, well, I'll end lecture here and we'll do this lab thing next. Okay, here's some calculations. In 1211, did you go over molarity? Did all of you go over molarity? I've decided to use these OpenStack books. And it's so weird, they exclude things. And chapter 1 through 10 should be 12, 11. I don't think molarity shows up there at all. So I'm teaching a 12, 11 class and using this, and I'm obviously going to have to supplement the book because chapters 1 through 9 are like missing important things. So molarity, we use a capital M. To denote molarity. And that's always moles of solutes over liters of solution. It's not liters of solvent. It's the solution after it's already made. It's kind of hard to predict, but the density will change. If I've got water and I've got some NaCl and I put the NaCl in the water, if I have exactly a liter of water when I put a bunch of NaCl in it, those ions have a tendency of pulling the water molecules close. So the actual volume of your solution will go down a little bit. So it changes the volume a little when you put a solute in a solvent. So it's liters of solution after it's made, after it's mixed, after it's homogeneous, and the moles of solute that you put in to begin with. We have what's that? Mole fraction. I'm going to say moles of moles of A, because you can have a mole fraction for the solvent and you can have a mole fraction for the solute. You can calculate either one of them. So let's say you've got V equals, you can calculate either one. Moles total of A and B. Total mole of all components. Of course, you can put more things together, so you can have all components. We'll tend to just do what we call binary mixtures, where you've got a solvent and a solute. But that's how you calculate that. I use kind of a fancy X for that. And A means, okay, that's the mole fraction of A. And you can also have moles of B. And then there's molality. And these are useful for some calculations we'll do. There's mole fraction. Molality and kilograms of solvent. So the denominator here is a little different from this one. This is exactly how much solvent you use and then the moles of the solute. That's not kilograms of the overall, that's kilograms of just the solvent. So the examples, I guess I'll do these. So if you go to the book, 11.3, 11.4, and 11.5, I kind of skipped electrolytes for now, because I think chapter 11.1 and section 11.3 kind of cover it.
What did you say you skipped?
Electrolytes. 11.2, but I'll come back to it. I just think section 11.1 and 11.3 fit together better. Electrolytes is kind of a digression. I'm looking for 11.1. I know it exists. So it's, there's 11.1. Yeah. Lost my mind. There. Oh, 11.3. Yeah, 11.3 is. Let's just start with 11.3, 11.4, and 11.5 next time. And what we'll do now is we'll do this lab. But first, let me show you this. If you go to the same place you go to find those quizzes to practice, in the form of a quiz, I've got two things. This is just a general quiz because we'll use it. So take that today and do. So let's see how this works. So if you open your book, you go to Experiment 1, laboratory safety rules. Start with welcome to the safety, welcome to the lab and safety. That's got all the information in it, and there's questions to answer, and then you come to do our lab 1. It has lab 1 questions like this. I think all that information is in that first module. And then there's a web search thing to do. You'll need to look at Appendix D here. Then, skepsis. Okay, these you should be able to upload a picture that you snap with your phone. So let's see how that works. I guess you just say add a file. I think y'all can do that. So go ahead and do that. Start with welcome to the lab and safety.